Did y'all read chapter 3? Nobody read it at all.
Well, I read it last time. I got it last time.
Oh, okay. Awesome. You did do the questions? Any of them stand out to you? Tell me about the closed, isolated, and open system. Closed, isolated, and open system. What's a closed system? What's the difference between a closed and an isolated system? It has to do with matter and energy. Has that it? Yeah, you're right. I think you're right. What did you say? Okay, that's true about a closed system. But what else is true about a closed system? No mass entering or leaving the system. So the universe, for example, is effectively a closed system. It has no energy or mass entering or leaving the system. And then an isolated system is one in which what doesn't enter or leave the system. An isolated can have energy coming in or out, but it doesn't have mass going in. And in an open system, it's just whatever. It transfers both matter and energy. It talks about the state functions. The state functions are the pressure, density, temperature, volume, enthalpy, internal energy, gives free energy, and entropy. We'll talk about the pressure, volume, temperature, and entropy today. And then the process functions, Arbeiter's terms. And then the zeroth, first and second laws of thermodynamics. The zeroth is that you have two objects that are in contact, they will come into equilibrium with one another eventually. The first law of thermodynamics has to do with the total internal energy of the system, that it can be worked on and it changes the energy. That's basically just restating the conservation of energy. And then the third, and in the context of that, we'll calorimetry. And then the third law has to do with the second law has to do with heat exchange and entropy. All right. We'll also look at PV diagrams again. We looked at PV diagrams last time. You should really know how to interpret a PV diagram. It's not that hard once you know it, but for the MCAT, you should certainly know how to do that. All right, so first of all, temperature scales. Temperature scales. We have 3 temperature scales. We have the Kelvin, degrees Celsius, and degrees Fahrenheit. These are all based on different physical quantities. So for example, the Celsius scale has a temperature that's set for the freezing point of water. This is the freezing point, and a temperature that's set for the boiling point of water. And on the Celsius scale, the boiling point is 100 degrees Celsius. The freezing point is 0 degrees Celsius. Similarly, for the Fahrenheit scales, they have temperature set for the boiling point and the freezing point. What's the freezing point in Fahrenheit? It's 32 degrees Fahrenheit. The boiling point is 212. Yes, thank you. 212. So notice that the difference in the temperature for these or the difference in a degree is different for the Celsius and the Celsius and the Fahrenheit. Which one has a bigger change in temperature for 1 degree, Celsius or Fahrenheit? If I change 1 degree Celsius, is that a bigger or smaller change in temperature than 1 degree Fahrenheit? Okay, well look, there are 100 degrees between 0 and 100. Between those same physical temperatures, there are 180 degrees between here and here. So I have 100 degrees here, or that's 3, but you get the idea. And then here, I have 212 degrees. I have more degrees. So which one has the bigger change in temperature for 1 degree, Celsius or Fahrenheit? Celsius. Okay, so if I have a change in temperature here, this is 1 degree Celsius, all the way up to 100, but a Fahrenheit degree is a lot smaller. In fact, a Fahrenheit degree is about half as small as a Celsius degree. It's 5 9ths. That's where that formula comes from. You have those formula in your book. I'm not going to write them down. frankly, you're probably not really going to see them. If you do see them, they'll probably just give them to you if you need to convert between Kelvin and Celsius. So I'm not going to worry too much about that. Then the Kelvin scale is based on some different temperatures. So this is Celsius, this is Fahrenheit. The Kelvin scale goes from absolute 0 up to just a little bit above the freezing point of water. This is actually the triple point of water. The triple point of water is that temperature, pressure, where you can have water in all three phases, in gas, liquid, and vapor. So the triple point of water, which is at about 0.01 degrees Celsius, is your standard for Kelvin degrees. And we have this difference here is about 273 degrees. 1 Kelvin, or a change in temperature of 1 Kelvin, is equal to 1 degree Celsius. Not that 1 Kelvin, not the temperature 1 Kelvin is equal to 1 degree Celsius, but these are equal sized degrees, unlike the Celsius and the Fahrenheit. So just sort of, have a familiarity with the temperature scales, what they are and how they're different, and then roughly how to translate back and forth between them. The formulae are in your book, just know how to use those, but I don't know that you should really know how to, know how to memorize. I don't think you really need to memorize them. Thermal expansion. Actually, let's first list the Zeroth Law of Thermodynamics. This just says that if you have one object that's in thermal equilibrium with another object, say I have an object A, and it's touching an object B, and they're in thermal equilibrium. When we say two things are in thermal equilibrium, that means there's no heat exchange between them, and it's just sort of a fancy way of saying that they have the same what, if you're in thermal equilibrium. Same temperature, right? So if they're in thermal equilibrium, they have the same temperature. So if A and B are in thermal equilibrium, and also B and C, these two objects B and C are in thermal equilibrium, and the Zeroth Law says that A is in thermal equilibrium with C. That should be fairly obvious. Basically, if A and B have the same temperature, and B and C have the same temperature, then A and C have the same temperature. And there's no energy flow between any of those. So that's the Zeroth Law. Thermal expansion. Thermal expansion is has to do when you heat things up, they get bigger. We did this in class last semester, but if you recall, delta L is equal to alpha L naught delta T. So if I have an object that has a length of L naught, that's its original length, and it has a temperature T, if I heat it up a certain amount by delta T, then that object will get bigger. And this distance that it gets bigger is delta L. If I heat it up, it gets longer. You can also have this with area expansion and volume expansion. And volume expansion is really a little more realistic, because volume expansion, as your book talks about, is the process by which we measure a temperature. And so the volume expansion looks very similar. It says that delta V is equal to beta V delta T. This is the coefficient of volume expansion. And it's just a constant for a given gas, liquid, or solid. If I heat it up by a certain temperature, if it has an original volume, this is going to be its change in volume. So that's volume expansion. Let's do a few other questions, and then we'll go into systems. Oh, shoot. Let me just give you, so you have your handout, right? Now let's go on to the systems, and then we have a bunch of questions about that. All right, so let's go on to the systems. You have three types of systems. And this might seem silly, but it's actually fairly important that you, like, it might seem just
why do you even care about these different types of systems? But it does pop up in my practice test, the different types of systems. So I would know them if you have room in your minds for it. An isolated system, you have a closed system, and then you have an open system. In the isolated system, no energy or matter is exchanged. With the surroundings. And so a good example of a true isolated system is our universe, because the universe presumably sits in nothing, and there's no energy then that it shares with its surroundings, nor is there any matter that's shared with its surroundings. Though this, it's actually kind of a debate. If you have things that go into a black hole, then it's thought that those things leave the universe. That's all theoretical, but the way mathematicians and cosmologists think about it, they think about it as leaving the universe. And then so by that you would say that the universe is not in fact a closed system, or an isolated system. Or something, yes. Yeah. A closed system is you can exchange energy but not mass. And in an open system, you can exchange both energy and mass. And the really important one for us is this middle one, the closed system. Because as we work with PV diagrams, we'll have systems of gas, where we put energy into those systems, or we take energy out of those systems, but we don't change any of the mass. And that's our work, our PV diagrams that we dealt with last time. All right, and then they talk about the difference between state functions and process functions. As I said, the state functions are sort of properties of the system, and those include things like pressure, volume, temperature, and then they give some other things there on 86. And then process functions are things that that take you from one state to another, that would take you from, say, one pressure to another pressure. And those process functions are working, for example. All right? So state describes the state of the matter, and the process describes the way you get to that particular state. You do work on a system to change its temperature, or you put heat in a system to change its temperature. You do work on a system to change its pressure or volume, for example. Let's put that down in words right quick. So state function describes the state of the matter. Pressure, volume, temperature, on and on. The process functions describe how you get to that state. So they describe the process to get to the state. For example, work, heat. If I do work on an object, I change its pressure and or its volume. If I do heat, if I put heat into an object, I change its temperature. So those are different kind of state functions and process functions. Now the first law of thermodynamics is really just a restating of the conservation of energy. And the first law says, oh wait, no, now I have some questions. So I think I have questions now, is that right? Yeah, so let's look. We're going to do number 1 on the first one. Y'all go ahead and do that. Look at number 1. And I have to pick up the files, so I forgot to bring them with me. So do number 1, and then do number 296, 297, and 300, and 313. Okay, so these first 4 on the second page. Do number 1 on the first page, and then 296 through 313 on the next page. And I will pull up the actual file. Run down to my office here. All right, let's try this first one. All right, it's an object with an initial temperature of 300, increases by 1 degree Celsius every minute. How many degrees Fahrenheit will its temperature have increased in 10 minutes? So go ahead and do that one, and then we'll go to the back page, 296 through 313. So a few more seconds. Everybody have their clicker for this? All right, going away. Awesome. Let's see, D for 10 minutes, 1 degree, that would be 10 degrees, 10 degrees Celsius, and now I'm looking for it in Fahrenheit, it's going to be 18 degrees. Because if I go up 10 degrees Celsius, remember a degree Fahrenheit is about half of Celsius, and so it's going to change a much larger amount in the Fahrenheit. That's all I'm saying. If I change by 10 degrees Celsius, then I change by roughly 20 degrees Fahrenheit. Those are the same changes in temperature. So C is the right answer. Let's try the next, on the next page. Number 296. In an isolated system, which of these can be exchanged with its surroundings in the system? This is number 296. Right here. All right, just a few more seconds. Stop at 20. Everybody. Okay, isolated, yeah, neither matter nor energy is correct, so D is right. It's just based on the definition. Let's do the next one, 297. In a closed system, what can be exchanged? What's the difference between an isolated and a closed system? A is right, only energy, and that's what we'll be dealing with today. And then a person blows air into a balloon. The gas in the balloon is what kind of system? Number 300 here. All right, just a few more seconds. Awesome. And that is an open system because I'm putting matter into it. And presumably I'm putting energy into it as well. But if I'm putting matter into it, that is a open system. And let's try this number 313. Which of the following properties are state functions? Temperature, heat, or work? Number 313. There are differences between state and process functions. So a few more seconds. Okay, which is heat? Is that a state function? No, that's a process function. That's the way you change the state. The state functions include temperature, pressure, and volume, and then entropy, enthalpy, there are 2 others. Okay? Y'all cover that in the chemistry section? You did? Okay. All right, and we'll come back to these. Okay, so the first law of thermodynamics is really just a restating of the conservation of energy. And it just says, if we're looking at it in terms of an equation, it's going to be the change in the internal energy is equal to the heat that's put into the system minus the work that is done by the system. So this is the change in the internal energy. Remember that internal energy is the energy of the molecules as they're moving around. So if you have a gas, the molecules are physically moving around, and they have a certain amount of internal energy. You can determine that classically just by the kinetic energy of all the different particles, and that's why they typically do that. And then this is the heat transferred into the system. And then this is the work done by the system. All right, they have a table on page 88 that describes the different signs. So here I have a positive value for delta U. That means I'm increasing in temperature. The internal energy, those molecules are physically moving around more, and so I'm increasing the temperature. If I have a negative value for delta U, then they're not moving around as much. That energy is decreasing, and so the temperature is also decreasing. A positive Q means heat is flowing into the system. Negative Q means it's flowing out of the system. And then the work, if you have a positive value, this is probably the most confusing, because I think the Q stuff is kind of intuitive, right? If I have a positive Q, I'm putting heat in. If I have a negative Q, I'm taking heat out. But the signs for the work is a little bit confusing. Work is done by the system if it's expanding. That is, work is positive if delta V is positive. Work is positive if delta V is positive. And if delta V is negative, then I have a negative work. So if my system is getting bigger, if the volume is increasing, if it's expanding, then I'm doing positive work, or the system is doing positive work. If it's getting smaller, then the system is doing negative work. You can sort of think about this, like think of like an engine, right? You have a piston with gas inside of it. It expands, the volume expands. That system is doing work. It's doing positive work. But if it's actually compressing, that means the system is doing negative work. It means like it's taking energy from somewhere else. Like with your car engine, your piston, when it compresses that gas, then I'm getting negative work. These are important because they'll be important in how we interpret PV diagrams, pressure volume diagrams. We'll get into PV diagrams soon, but let's start next talk about heat. Heat transfer. This is, when we talk about heat, we'll talk about Q. Now, you might be confused and think, well, heat, that sounds a lot like the internal energy, but it's not. Heat includes the flow of energy, while internal energy means the energy of the motion of all the molecules. So while they are related, heat always refers to the flow of energy between two places. So that energy will always flow from a warmer temperature to a cooler temperature, and your book talks about that. The units that we use for it are energy units, so we'll use joules or calories. Either one. Joules is the SI unit, but people often use calories for this. I don't know why. It's the British unit, but we often use calories. And a calorie is one big calorie, that's a food calorie, is equal to 1,000 calories, is equal to, what was it, 4184, I think. Yeah, 4184 joules. I don't think you need to know that conversion factor, but just know that it exists. You can have different types of heat transfer. You can have conduction, convection, or radiation. Conduction requires what, John? If I have conduction of heat between two objects, what must be true about those objects? I think you know this sort of intuitively just from the word. What must happen in order for heat? They have to be touching, yeah. So in order for two objects to transfer of heat by conduction, they have to be touchy. What is convection? What is required when we have convection? I have to have the motion of a fluid. So convection occurs whenever I have motion of a fluid, like a convection oven. What does a convection oven have inside of it? You don't know? You don't have a convection oven? We don't either. It has a fan inside of it. So it's just like a regular oven, but it has a fan. And the fan just blows air through your oven and causes the heat to transfer to the food more readily. And that's why they cook faster, the convection oven. And then the third thing is radiation. And radiation occurs just by electromagnetic radiation. So for example, we receive radiation from the sun. That's what heats the earth. That's the primary means of getting energy, or that's the only means that we have of getting energy from the sun. Because we don't touch the sun, obviously. And there's also no fluids between here and the sun, except for our atmosphere, but none in the intervening space between us and the sun. So those are three different ways of conducting heat. Specific heat, and this is where we get into calorimetry, is a description of a material that says how much energy is required to raise the temperature of that substance by a certain amount. It answers this question: how much energy is required to raise the temperature of a substance by a certain amount. All right, y'all know what the specific heat of water is? It's 1, right? The specific heat of water is 1 calorie per gram degree Celsius. That means that it takes 1 calorie to raise 1 gram of water by 1 degree Celsius. Right? That is specific heat, and it comes into play when I want to determine how much heat flow is required to raise the temperature of a substance by a certain amount. So if I want to know how much heat must flow into a system to change it by this temperature, this is my mass, this is going to be my specific heat. Okay. And as I said, the specific heat of water is equal to 1 calorie per gram degree Celsius. It takes 1 calorie to raise 1 gram of water by 1 degree Celsius. Let's see, I think I might have had a question here. No, we'll come back to these. All right, we can also have changes in phase. And these are described by the latent heats. Is the energy required to change a material's phase. You know, from solid, liquid to gas. And so if we make a plot here, I don't think this was in your book, but if we make a plot of temperature and energy, or Q, the heat that we put into it, take, for example, water. Let's say that I start with ice down here. We'll call this 0 degrees Celsius. So I'm at sub-zero ice down here, and I put heat into it, and it's going to raise the temperature of that ice. It's going to raise it up to a certain point, and then the diagram, or it'll sort of plateau out the temperature, and your diagram will look like this. I'll explain what these mean. So, I have sub-zero ice right here. If I put heat into it, what happens to the ice? It does what? It doesn't melt yet. Right here I have it, say, minus 20 degrees Celsius. I put heat into it until it gets up to this temperature at 0 degrees Celsius. Right? So it's just raising temperature. So if I want to know the amount of heat required to raise that temperature, then I would say this Q equals mc delta T. Now here is changing of phase. So it takes a lot of energy actually to change a solid into a liquid, apart from changing its temperature. If I have 0 degree ice and I have 0 degree water, I still have to put in energy to change all of that ice to water, still at 0 degrees. So you can have water at 0 degrees, but it not be ice, right? If you have a cup of ice water, you have ice at 0 degrees and you have water at 0 degrees. They're both at 0 degrees because they're in thermal equilibrium, but the ice is 0 degrees and the water is 0 degrees, but the water is not turning into ice. Now, if you continue taking away energy from it, it will, but in a cup of water, of course, it doesn't. So here, I have ice. Here, I have ice plus water. Now, the energy here that's required to change my ice into water is this latent heat. Its Q is equal to the M times the latent heat of fusion. So this is the amount of energy to turn water into ice into water or water into ice, or some other solid into a liquid. This is called the latent heat of fusion. You should have done this in chemistry, first or second semester of chemistry, right? Yes. Okay. So that's your latent heat of fusion. The energy required to go from here to here. Then I take my ice, I raise its temperature, and then here I have 100-degree water. Over here I'll have 100-degree steam. This is called our latent heat of vaporization. I keep these separate in my mind because, a vapor is a gas, and fusion is like when I fuse two things together like in a solid, and I make them solid together. So that's my latent heat of vaporization. The amount of energy required to change a certain mass of liquid into a vapor is this mass times the latent heat of vaporization. All right, let's try a couple quicker questions. Let's try this number 5 here. This is actually in your book, but please don't look in the back. Number 5, how much heat is required to melt 500-gram gold earrings given their initial temperature? And it gives their various melting points and stuff. All right, just a few more seconds. Guess if you're not sure, I'm going to, the 5th one, go ahead and get your answer in. I'm going to start here. First thing we want to do is figure out the temperature required to get it up to a certain, or the energy required to get it up to 1064 degrees Celsius, which is the melting point. So that's going to be the mass, which is 0.5 kilograms, times the specific heat, which is 126, times the change in temperature. Now remember, my change in temperature, the temperature here is given in Celsius, but a degree Celsius is the same as a degree Kelvin. So as long as I'm talking about differences in temperature, I don't need to worry about my units here. I can just, a change in Celsius temperature is the same as a change in Kelvin temperature. So I have 1063 minus 25, or 1064 minus 25. All right, so that's going to be what? About 63 times 1040. So that's about 63,000 joules, or 63 kilojoules. But then I also need to figure out how much energy is required. I'm going to go and stop this. I get 6 people. Okay. Then I want to figure out the amount of energy required to change it into a liquid. So I have 63,700 joules per kilogram. That's my latent heat of fusion. And then this mass, so it's going to be 0.5 kilograms times 60, I'll just call it 64,000. That's equal to 32,000 joules, or 32 kilojoules. All right, so I add this 63 and this 32, and D is the right answer. It's a good basic calorimetry problem, but also with this change in phase. I first have to figure out the heat required to change its temperature, and then the heat required to change its phase. So D is the right answer. Let's do this number 94. And then after that, we'll come back down to number 2. So after you do number 4, 94 up here, come back and do this one. And I'll put up the liquid first. All right, just a few more seconds. Let's see, is that right? A? Yep, that's right. Melting of a solid has to do with the heat of fusion. So A is right. All these other things are something different. So this would be sublimation of a solid. That's when it goes from a liquid to a vapor. That's something different. I'm not going to deal with that. Boiling of a liquid means that you bring it up to the boiling point, but you don't change its phase. And then condensation of a gas, like when you sweat and it evaporates off your body, this would be the latent heat of vaporization. Would be relevant there. All right, and now let's do number 2. It's number 2 down here. What are these different heat transfer processes? All right, just a couple more seconds. Awesome, A is right. Radiation from the sun to the earth. Metal spoon is conduction because it's touching, and then a rising plume of smoke from a fire is going to be convection because you have this gas that's moving, this fluid that's moving. All right. About number 311 down here, the one about Madame Curie. Go ahead and click in with your answer, number 311, the one about Madame Curie. All right, just a couple of seconds. Okay, great job, y'all. So that was convection. Yeah, convection. So by putting the cup on your coffee, you keep the air above it from moving around. the next time you go to McDonald's and say, hey, I'm a cup or a cap for my coffee. I got to deal with that whole convection thing. Okay? Put that in the all right. Let's see. There's some more here on calorimetry, but I'll let you deal with that. Let's get into PV diagrams. It's fairly important that you know how to interpret PV diagrams. In your book, they describe different processes. These isothermal are same temperature. Isothermal means the temperature remains the same, or your delta U is equal to 0. So the change in the internal energy of your system does not change. And we have adiabatic. That means that you're not putting any heat into the system. So my Q here is equal to 0. There's a table, by the way, on page 93 for this. And then you have isobaric. This means constant pressure. And isovolumetric, or isovolumic, is constant volume. All right, or let's see, they also call it isochoric. I don't know where that comes from. But the other words sort of hint to them, at least these three iso words hint to what it means. Isothermal means my temperature doesn't change. Thermal, think about temperature, I think about internal energy. My delta U is equal to 0. Isobaric, think barometric pressure, right? Have a constant pressure. And then isovolumetric or isovolumic means I have constant volume. And if I plot my PV diagram, I'm going to have my pressure here and my volume here. You can also have temperature on the x-axis, and they give pictures of what these look like. So for example, this is an isobaric because the pressure remains the same. This is isovolumic, and then they also give adiabatic isothermal curves as well. But those are in your book on page 93. You should look over those and just make sure that you know what those four terms mean. So if you encounter them, you'll know. Let's look at a PV diagram. There's an example on page 94 where I can show you how to find the work that's done by or on a system. But let's say that I have a PV diagram and I go from this state to this state, from A to B. If I want to know the work that's done on that system, the work is equal to P times delta V. If my delta V is positive, is the system doing work, or is it having work done onto it? If my system is expanding, is the system doing work? That is, work will be positive, or is work being done to it? If the volume is getting bigger, it is doing work. Like think the piston in the engine. When the volume expands, that means that the gas is doing work. The system is doing work. So in this case, I'm going to have a positive work because delta V is positive. My volume is getting bigger. This is an expansion. And I know it's an expansion, y'all, because look, I start at one volume down here and I get bigger. So my volume is getting bigger when I go from point A to B. And so if I want to know the total work done, I just take the area under this PV diagram. We did this last time. I just find the area under the PV diagram. Now in order to do this, you have to break it up into two spots. You'll have a rectangle on the bottom and a triangle on the top. And remember that the triangle is 1/2 based on height. Let's do a couple of these. I gave you some in your handout. There's a little passage problem at the back, or where you have this diagram and you have to interpret it. Notice here on this, I have my pressure in pascals, that's the SI unit, volume in cubic meters, and then I have different points, A through F. Let's start with problem number 336. Approximately, what is the net work done on the gas as it goes directly from state F to state A? So I'm going from here to here. What is the work that's done on this gas going from F to A? You have to be very careful when you're reading these problems. I'm going to stop it for a second. Let me point out something. Be careful. It says, what is the net work done on the gas? That's different from the work done by the gas. So when we're talking about that whole positive, negative thing, that's when we talk about the work that's done by the gas. If it gets bigger, then the gas is doing positive work. If it gets smaller, then the gas is doing negative work. But that's the work being done by the gas. This is actually asking for work done on the gas. So something else is doing work on this system. And the difference between by and on is a negative sign. So if I'm doing positive work, then my work is positive. But I'm doing negative work on some other system. Understand what I'm saying here? All right, so revisit your answer, and I'll show you what the answer is here. Or not, that's fine too. All right, I'll stop at 2 minutes, okay? Or 1:58. Okay, so to find the work, you find the area. Nice, easy way is just to count the squares. I have 16 squares. Each of those squares is 50 times 0.5, so each of those is 25 units. Y'all follow what I'm doing there? I have, on the y-axis, I have 50 Pascal. On the x-axis, I have 0.5. So these 16 squares all have 25 units. And so 16 times 25 is 400. So it is either A or C, but is it positive or negative? Now, the volume here is getting smaller, right? My volume is going from here to here, from F to A. So I would say that it's doing negative work, right? That there's negative work being done on the gas, except now it's asking for not the work done by the gas, but on the gas. So the answer here is I have positive work being done on the gas. Imagine if I have a cylinder, I'm pushing it down, I'm doing positive work on the gas, but there's negative work being done by the gas. It's a little confusing, yeah, so you have to sort of wrap your mind around it. The difference between on and by. But those are very important words for answering a question, because it will change the sign. And I think the MCAT folks, like, they would expect you to know the difference in those. That's not just trivia. All right, so here the answer was C. All right, approximately what is the net work done on the gas as it goes from state B to state C? Again, this is the work done on the gas, not by the gas. How long is this class? So remember, if my volume's getting bigger, my gas is doing positive work. But if the volume's getting bigger, the gas is having negative work done on it. Alright, I'm going to stop. Huh. Okay, it's not C. It's going to be A. I want to find the area under this section from here to here. And so I count the squares. I have 1, 2, 3, 4, 5, 6 squares. 1, 2, 3, 4, 5, 6, 7. So 7 times 6 is what? 42? Plus I have 1, 2, 3, 4, maybe another 5 or 6. So we'll just say it's approximately 50 squares times each one was worth 25. And what does that equal to? 50 times 25. It's about 12. What is that? 50 times 20. 1200, right? 1250. Yeah, so 1250. All right, so it's going to be approximately 1200 or so. I'm just estimating it, but look, it gets me darn close to the right answer. Just finding the area under that graph, and now I need to figure out, is this going to be positive or negative? Because I'm stuck now between A and B when I'm going from B to C. So my volume is getting bigger, but I'm looking for the work done on the gas. And so what's going to be positive or negative? It's going to be negative, yeah. So A is the right answer. Did I mark that? Yeah. Okay, now let's try 341. I'll stop in just a few seconds. Okay, which one were we doing? I missed 341, right? Okay, so B, C, D, E, and F, 341. The answer is, well, shoot, I don't have it. So I'm going from here, I'm going through C, through here, and through here. So in order to find this, I'm going to have to find two areas. I will find the area under BC like this. Didn't I already find that? That was 1200, right? Minus 1200. So that was minus 1200. And then I'm going to find the area here. What you're doing basically is you're finding the area inside this section right here. The area there is going to be, let's see, I have 1, 2, 3, 4, 5, 6, 12, about 15 squares. So 15 times 25. Yeah, something's funky going on.
Yeah, there's not 6 people in here even.
I know. I don't know what's going on. Something's weird going on over here too. That's going to be 250 plus 125 is about 375, I think, roughly. So I'm going to subtract or add that to my minus 1200. So this area is about 375. Didn't that do that right? It's at 250 plus 120. That's 375. Minus 1200 plus 375 is going to be my minus 950. So B is going to be the right answer. Okay. need to make sure you know how to do PV diagrams, that you can interpret them in that way and understand what they mean. If you don't have them, make sure that you go back and read those sections on PV diagrams. Okay, dokie. You feel like you can do a PV diagram if you saw one or encountered one? Megan?
Why did we like these guys count like a little triangle towards the left?
Because we are only going from B to F. You're right, if we were going from B all the way back to A.
It was back to A. Yeah.
Oh, okay, yeah, I'm sorry. Well, if we were doing that, yeah, I'm sorry. I just thought it said back to F. If it was to F, it would just be as we've done it. If it were going all the way back to A, you're right, Megan. I would find the area under this section and then subtract the area under this section. Okay? I'll leave you to do that on your own. But if it was from B to F, it would be this minus 950. What would it be? It might be similar if it's from from A to A. It might be the same. Not sure. There's a much easier problem in your book on page 106. It just gives a triangular system, and so the area is a lot easier to find. But you might encounter either on that. That's page number 6 on page 106. Okay? I'm going to skip over the entropy section. In the section on entropy, they get into the second law of thermodynamics, and it just says basically that in a system that your entropy will increase. That is, that the temperature will tend to, the internal energy of the system will tend to disperse. Like you have a cup of coffee in a room, the heat from that cup of coffee will tend to disperse out into the room. And that's always true. You're never going to have the reverse happen. That if you put a cup of coffee in a room, heat from the room will go into the cup of coffee. That's not going to happen. That's physically just not happen. So we're going to skip over that section, and we're going to go on into fluids, if that's okay. But if you have trouble with these PP diagrams, you need to go back and revisit them in the chapter, okay, and work some of the practice problems in the chapter. Well, let's go on to the next chapter, which is on fluids. Because next time we'll do our little exam. Like I said, maybe 10 questions, 15 questions, probably half hour I'll give you to take them. There'll be a couple passages there for you to take that'll cover energy, work, kinematics, force problems, stuff like that. And then you'll also probably have a thermodynamics problem as well, probably one of those PP diagrams. Okay? To prepare, just read through the chapters, look at some of the questions we answered in the past couple of class meetings. But let's go on to the next section. We're going to, a lot of this we've seen before. We did do this last semester. We had a chapter on fluids and solids and what have you. But just have some definitions that we need to do for fluids and solids. First of all, fluid, when I say fluid, I mean anything that flows. So that might mean a gas or a liquid. It can be either one. And then, of course, solid is a solid. When we're talking about both fluids and solids, we need to know the definition of the density, which is just mass per unit volume. Of course, you can have this in grams per cubic centimeter or kilograms per cubic meter. Either one of those is fine. But you do need to know how to convert back and forth between the units. And don't forget when you have these powered units that you have to do that cube thing for converting from cubic centimeters to cubic meters. They also give the specific gravity. We don't really use the specific gravity in physics, but I think that you might use it in chemistry. Is that right? You use specific gravity in some of your chemistry labs? You have, yeah. So the specific gravity is just the density of the material divided by the density of water, which is 1,000 kilograms per cubic meter. So the density of water is 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. You ever wonder why that's the case? Why is the density of water 1 gram per cubic centimeter? You ever wondered about this? You've probably seen this number before. Why do you think it's 1 gram per cubic centimeter? That seems curious, doesn't it? You don't know why? That's how we define what a gram is. We define it by, we take a cubic centimeter of water, and then that's a gram. That used to be the standard for the gram, like for the gram. They said, what is a cubic centimeter of water? That's a gram. And it's a similar thing with specific heat. That's how we define what a calorie is. That's why it only takes 1 calorie, exactly 1 calorie, because that's how we define a calorie. All right? I always thought that was, it's like, that seems strange. 1? What is 1 in the universe? Nothing's 1. Except for the density of water, it's 1. Okay? Pressure. Pressure is defined as a force per unit area. It can be in a bunch of different units. We can have newtons per square meter. It can also be in pascals. We can see it in millimeters of mercury. The millimeters of mercury comes about from our barometer, our manometer. We did that last semester, but we'll revisit it next time, how that unit comes about. Like when you're measuring blood pressure is measured in this millimeters of mercury. Right, you ever go to the doctor and get your blood pressure measured? They have that little thing, and you see the little mercury column going up. They're physically measuring what is the height of that column. And they also have it in atmospheres. Atmospheres is just the atmospheric pressure at sea level. We have absolute pressure versus gauge pressure. Now hang in there, just a few more minutes, we'll wrap up, okay? So, you measure the air pressure in your tire, it's what, roughly? The air pressure in your tire, what it should be? What's it? No, it's not 10. It's like 30 or 35 psi in your air in your tire. But what if you have no air in your tire? You come out and your tire's flat. What's your pressure in it then? It's the atmospheric pressure. But if you were to put your gauge on there, it would be what? It would be 0, right? So your absolute pressure, if you're looking at the absolute pressure of your flat tire, that would be atmospheric pressure, 1 times 10 to the 5th or whatever it is. If you're looking at the gauge pressure of your tire, that would be 0. All right, so absolute pressure is like the actual pressure. Gauge pressure is just what we measure it to be. Okay, let's look at Pascal's principle, and then we'll wrap it up, okay? Pascal's principle, I don't know if y'all recall. Pascal's principle says that if I have a change in pressure, so I have some pressure, I have this piston with a liquid in it, an incompressible fluid, which is a liquid, then if I have a change in pressure up here, I have that change in pressure at every point inside that piston or that container. And the great application of this is in hydraulic systems. Your book does an example like this. I have a certain force over here, F1. I have A1 here. I get a force out over here, F2. I have a bigger area, A2. This says that any change in pressure I have over here will equal the change in pressure I have over here. That P1 is equal to P2. That is F1 over A1 is equal to F2 over A2. So, because I have a big area over here, am I going to get a big or a small force out in comparison to F1? Bigger or smaller force compared to F1? It's going to be a lot bigger, depending on how big your area is. If your area is 10 times bigger, I get 10 times the force. So if I have a little bitty piston over here, like on your car jack, a bigger piston over here, I'm going to increase that force by quite a lot. All right, I'll bring some questions next time, and we'll do Archimedes' principle and fluid flow. Fluid flows are a big deal on the MCAT. I think because in the body there's a lot of fluid flows, but if you look in all the practice tests, there's almost always a fluid flow. So I certainly want to spend some time on it next time.
we did it pretty well last semester, so what we did in 101 last semester should help you a lot for that part of the test. Okie dokie. Y'all hang in there, okay? I know it's hard. It's like our numbers are waning. Y'all look like you're waning, but I know it's been a tough week. So, get a good weekend, get some good rest. Marty? EP? Where did you see that? Oh, extra practice quizzes. Those are your Moodle quizzes.